Okay, in this example, it says find the four fourth roots of 1 by two methods, the factorization method or factoring method, and by the nth roots method. Okay, so I think we're all pretty familiar with the factorization method, but let's just go ahead and do it. Okay, the factoring method, well, remember to solve this, we set up our what they're asking for, and it's going to look like this. Okay, we're going to always be starting from this. And so we have z to the nth equals c. Our c in this case is 1. Our n is, in this case, is going to be 4. Okay? So when it says find the four fourth roots of 1, this is really what it means. All right, so by factoring, I want to find the values of z that will make this statement true. So I'm going to go z to the fourth minus 1 equals 0. And now we can start factoring. So this is going to be z squared minus 1 times z squared plus 1 is 0. And this factors nicely into z minus 1, z plus 1. This actually will have complex roots, right? So we have z plus I and z minus I, and that is equal to 0. So there we have it. These are my four solutions. Z is equal to 1 minus 1 minus I and I, right? So these are my four solutions. Okay, so this is by factoring. Very straightforward, very familiar. Okay, let's try the nth roots method because this is the more general method that will work for any number that goes in here. Okay, if I had a plus bi, I could do the nth roots method. All right, so z to the fourth equals 1. Now, the nth roots method said, if you look back at your notes, we get c to be in polar form. So right now we have 1 here. Let's write that in polar form. What is that in polar form? Since 1 is over here, that would be z to the fourth is equal to cis of 0, right? Okay, and so now we have this, and then the next step is to use the property where this can keep spinning around for values of k, right? So we have z to the fourth is equal to cis of 0 plus 2 pi k. Okay, where k is a element, of integers. Okay, and then we want to get z by itself, and so we take the fourth root of both sides, and this becomes, okay, so this becomes 1. Since the magnitude is 1, that just stays 1, and this becomes cis of, here, I'll just write this whole thing out here. Okay, this whole thing becomes raised to the 1/4 power. And that becomes 1, okay? Using de Moivre's theorem now, that just becomes 1, and that becomes cis of 2 pi k. I'm going to get rid of that 0. 2 pi k over 4, which simplifies to cis of pi over 2k. All right? So this is the general solution. Okay, this is the general solution. Now all I need to do is plug in values of k. How many values of k do I need? I need 4 values of k, and they all have to be consecutive numbers. So I could start anywhere I wanted, but let's just start with 0 because that's probably the easiest one. So z, when k is 0, we're going to end up with cis of 0. When k is 1, cis of pi over 2. When k is 2, cis of pi. When k is 3, cis of 3 pi over 2. Okay, and those are now my four solutions. K is 0, k is 1, k is 2, k is 3. I could have picked any values of k I wanted because it'll always come back to one multiple of those, but we just started with 0. Okay, and now this becomes cis of 0. Well, that's just 1, isn't it? So that's just 1. Cis of pi over 2, that's over here. So that would be I. Cis of pi would be over here. That would be minus 1. And cis of 3 pi over 2 would be down here. And that would be minus I. Okay? So these, again, are my four solutions. These are the four numbers that if I raised them to the 4th power, I would get 1. Okay? And notice here that on the picture, whoops, that's not a very good circle, they all lie on a circle of radius 1 because the 1 is the modulus of 1 raised to the 1 over 4 power. Okay?